I'm going to have functions of 1/2 x. But don't I really want functions of x at the end? I mean, wouldn't that be easier to work with? Whenever you're working with trig, your final answer, you really don't want it to have a different argument than the question. There's no advantage to that. It's kind of tricky. So there is one really, really simple trig identity that I'm going to show you. And by the way, the very few books that this is in, it's as if the authors didn't know there was actually a trig identity. So every single answer to every single question in every book, and even if you go online, they'll give you answers in 1/2 x, which is not helpful. I need answers in x. So, I guess I can write here. It's there is a double angle formula for tangent also. And the one we're going to use is real simple. The tangent of 1/2 x is 1 minus cos x over sine x. That's always true. Huh. It'll make it easier than that. Can I split those up? I'd rather not have a quotient. What do I have? 1 over sine, which is cosecant, minus cosine over sine, which is cotangent. As awful as that is, that's the simplest substitution to get me back to x's. Your two favorite functions, right? Cosecant and cotangent. No, it's a big yuck. But it means at the end of the problem, I will have a function of x rather than a function of 1/2 x. The reason you changed it in Calc 1 when you did a u sub, because the function of u doesn't help me answer the question if I'm looking for an antiderivative. But if I was substituting back and I didn't have x, but I had some version of x, it's not as helpful. So let's now attack that problem right there. This is, by the way, that's just generic. I can change infinitely many. I can throw coefficients on these guys. I don't need coefficients. So here's how we're going to start the problem. We're going to start the problem by saying, let u equal this. Then all of these things are true. I don't need to write all those down right now. I'm going to start by saying, let u equal this. Otherwise, how the heck am I going to replace tan x with that quotient? Tan x is never going to equal that quotient unless that's a true statement. So I have to state that to start the problem, but it also tells me when I'm done, how do I go backwards? So what will this become? I'm going to replace tangent with, where is it over there? 2u over 1 minus u squared. I'm going to replace sine with 2u over 1 plus u squared. The dx is 2 over 1 plus u squared. By the way, you could put it here or you could put it here. It doesn't really matter. Now, right now this looks terrible. Do you agree that we're going to clean this up and make it into one quotient at some point? But now that will be a rational function. And I'm guaranteeing you, you will be able to integrate that using nothing more than what you already know. At worst, parts. Probably more like a partial fractions. It might be the quadratic form where I had to add and subtract, like we did last day, inverse tan. It could be any of those, but it's gonna be a rational function. So off to the side, let's clean this up, okay? So let's start with the denominator. I've got 2u over 1 minus u squared plus 2u over 1 plus u squared. So let's, yes, I can cancel one of the denominators with the numerator, but then that doesn't, I'm going to end up doing all the same work anyway. So if I put these over a common denominator, then won't this be 2u times 1 plus u squared plus 2u times 1 minus u squared all over 1 minus u squared, 1 plus u squared. We agree with that? So on top I'd have 2u plus 2u cubed plus 2u minus 2u cubed. Ooh, I like that. So now I have 4u on top, 1 minus u squared, 1 plus u squared on the bottom. Okay? So my overall quotient is 2 over 1 plus u squared divided by all of this, or times what? the reciprocal. Well, that don't seem so bad. What do I have now? Oh heck, I even do 2 and the 4. So what do I have right now? I have 1 minus u squared over 2u. Can I pull the half in front? Might make it easier to work with. So if I split this up, okay, I'm going to pull the half in front and write it as 1/2 times. And no, I don't want to factor the top. I want it like that. What does that leave me with? 1/2 of what?
Negative u.
Well,
1 over
1/u.
minus u.
And by the way, that's my integrand now. Woo! So all of that horribleness over there reduce all the way down into that. That's pretty friendly, wouldn't you say? Now, is it always going to reduce this nicely? No. If I throw coefficients on those guys, this is probably a lot uglier because you're not going to get all the canceling and combining that you got there. But it doesn't matter. The process is still exactly the same. You're interested in the process more than the answer at this point. So all of that stuff, we can say that this is identically equal to 1/2 the integral of 1 over u, what is it, minus or plus? So, minus u. Wow. I like that problem. All right, let's integrate that.
1/2 ln u minus.
At this point, yeah, I'd probably go ahead and distribute the half because I've already got fractions. That's really not the issue. That's pretty friendly. Now, do I need the absolute value? U equals the tangent function. How often is the tangent function negative? Half the time. So do I need the absolute value? Yeah. Okay? But remember, you're going to replace, not with tangent of a half x, you're going to replace it with what? Cosecant minus cotan? That's pretty awful. Do we agree? That's awful. We can check through differentiation. It might take us longer than the original problem. No, this is where I use technology to check my derivative. If we made an error, it's more likely to be a coefficient or a plus or minus sign. Okay? But what I would do is I would go to Wolfram and I'd just say, differentiate this. And the nice thing is you just write literally differentiate and you type it in and you hit E. It will not give you weird answers on derivatives. It only gives you weird answers on integrals. And what are you hoping to see on your screen after you hit enter? That function right there. And if you do, then you know you did it right. If you don't, you have an error. I think it is, okay, everybody knows this in any math class. When you're practicing problems and you're looking at the answers in the back of the book, most books have all the odd answers, right? So should you practice the even problems at all? Simple answer. I tell people, why would you waste your time? Because you cannot check your answers. Now, there are maybe other ways to check an answer, but I think it's foolish to practice any problems if you can't check your results. You know, you're doing 5 hours of math homework. Gee, I hope I was right on those. No, I need to know if I'm right or not. Now, the problem with most of using the textbooks, right? In the back of the book, it was the answer was x equal 4, and you got x equal 5. Great. I'm incorrect. Do you know where you're incorrect? No, because that's not a solution, it's just the answer. So a lot of times textbooks come with a solutions manual. Now, most of the calculus books used to, but the solutions manual isn't every other problem. Might be every 5th problem or every 10th problem, because it takes too long. For those of you who are in the discrete math class, a couple of you, the solutions in the back of the book, they're random, but maybe it's not every other problem. But there are a lot of solutions, and it's detailed. That's what you need. You don't want the final answer, because if you don't get that, you don't know where your error was. But at least it's better than not having anything. So if you did it right, at least, okay, I did it right, I got the same thing. It's only invaluable if you didn't do it right, you don't know. But if you don't have any way of checking. So when you're doing the calculus stuff, the check is actually, I take the derivative of this, do I get back the integral? That's the only check. The check isn't do the problem again from beginning to end. Now, I checked this, I didn't get that back again. Does that mean I scrapped the whole problem? No, it means I go through and I say, oh, you know, when we were doing this, I think I lost a 2 somewhere, and someone pointed out I lost a 2. Well, when I'm doing this problem, if I lose a 2, am I going to get the right answer? No. But then I go back and I find that missing 2, and I go back and finish it. That's kind of the order of things. So now you know why I affectionately call this the evil trig. You ask anybody in Calc 3 or higher about the evil trig, they'll say, yeah. Does it come up a lot? No. It does not come up very often at all. But if it does come up, I'm in physics. I need an antiderivative of this because I need to evaluate it maybe at multiple places. There's no technology on planet Earth that's going to help me give numerical values to things when I don't have an actual function. I need this in order to work with and evaluate. And maybe I have to consider what the graph looks like. Maybe I'm doing some stuff, but that can be evaluated. Now, I can make that problem worse. Coefficients usually make it worse. But if I make it worse, it only means that the rational function won't clean up this nicely. Now it's going to be one of the other techniques you've already used. So let's do another one, and I'm not interested in the answer. We were able to answer this easily because this reduced all the way to here. But it was really, this is the part I cared the most about. If you can state this correctly, you can now proceed. If I don't get this correct, right, then it doesn't matter because I'm doing a different problem. So let's take something like this. You don't have any techniques per se that will address this. Okay, I can't use any Pythagorean things because of that 2. That messes me up. Multiplying by the conjugate won't help. Well, what if I multiply by a 2 plus? Then I'd have 4 minus cos squared, and there's no identity there. Only 1 minus cos squared would have an identity. So we're going to use this process. And my very first step would be to say, let u equal tan half x. You have all that. You might not use all of those. Am I going to use all of those in this problem? On the far right, am I going to use all of them? Exactly how many of those am I going to use? I'm going to use the cos and the dx. That's it. That's all I need. But I'm going to have those because I don't want to have to, gosh, I never would have to rederive these. If you're asking me, do I remember these between semesters? No. Why? Because they just don't come up very often. I just rederive them every time we do this. Because they just don't come up very often. But if they do come up, I want to have them. Now, let's suppose what I'm doing, these come up a lot. Well, then I'm going to remember all those because I'm using them all the time. That's how it works. How many here are engineering bound? How many are not engineering bound? That maybe it's easier. Okay, a few of you. So you're an engineer. Does an engineer know every single calculus formula, every single physics equation? And by the way, you guys have to do a lot of chemistry. Every known published chemical reaction. My closest friend in grad school was a chemist, and I said, well, how much of that do you know? He's like 1%. I mean, there are literally tens of thousands of known chemical reactions that are posted. Do you guys still use something called the CRC manual in physics? When I took physics, the CRC manual was a book, and every year you had to buy a new one, with every published mathematical formula, chemical reaction, and physics formula. And it was a big, thick book. Every known chemical reaction. There was more chemical reactions than anything else. Why is it important? Well, my closest friend was, we were grad students together at UCSD. I was in math, he was in chemistry, and he worked in a lab 60, 70, 80 hours a week. That's all he did. It was just lab work and research. And I said, why is this important? He laughed, he goes, well, because before I go do a reaction, I want to know if anybody's ever done it before. Why? Because I want to know if I'm going to blow up or not. It's kind of how he put it. In other words, if the reaction is known and you look at the heat exchange is 1,000 degrees, that's probably not good, right? Remember your delta H in chemistry? You know, if it's 1,000 degrees, that means everybody's melted and evaporated. So that's probably not one I want to do. Every known chemical reaction was published. Then if he was going to do one that's already been done, he can look it up so he knows what he's going to get. What if he's doing one that's never been done? Ooh, it could be a little nerve-wracking perhaps. Okay? Well, that's the same idea. You know where to find the answers, but does anybody know all of these? Oh, heck no. Which ones do you know? I already give you a hint. Which ones do you know?
The ones you use the
The
most.
ones you use. And you know where to find the rest. I have had many students over the years tell me about their job interviews. I had somebody tell me just last year, I had so much fun with this one. And I think they ended up getting a job, just not this one. So they're going to the job interview, and there's, of course, the long table of scary-looking people, right? And they ask you questions. They don't give you a sheet of problems and say, do this. No, they ask you questions because they want to see your problem-solving ability. You've graduated. They know you have a degree. The one thing that never comes up in any application is your GPA. They want to know, okay, you graduate, you have the proper background, do you have any work experience, can you think? So they asked him a question, and I don't remember the nature of it. It was something where you had to use some math and thinking, and he said, hold on a minute. And he pulled out his cell phone, and he started doing this. And after about 30 seconds, they said, thank you, and they dismissed him. And he couldn't believe that he was looking up, because of course that's what you do. You look up the answer on your cell phone. They basically had a good laugh, like, this may be the dumbest person we've ever interviewed, because not only did they have no idea how to even start the problem, they thought that they could look up the answer during the interview and then just regurgitate the answer on their cell phone. And so he did get another interview, and he realized that probably wasn't a good move. They wanted to know if he could think on his feet. That's called problem solving. Now, what if the question is so obscure that really you wouldn't know it? You know how to find it, but it wasn't an obscure question. It was just one he didn't remember how to do. And it was one he said later, yeah, I probably should have known how to do that. You know, it probably came straight out of, Physics 195 or something. But the idea is, you know what you know. You know what you use all the time, and you know how to find the obscure ones. Everybody worries in a class like this about the obscure stuff. No, don't worry about the obscure stuff. Worry about the stuff you're supposed to know, right? Sines, cosines, exponentials, polynomials, that's what comes up over and over and over and over again. If you're struggling at those, then you're in trouble, because those are the generic all the time. The more fringe ones, you're saying, there are some that come up that we don't use all the time, but I am aware of how to answer them. That's why I said always have your integration sheet, right, that I put out. Have that in front of you at all times, just in case something is on the edge and you don't know it inside out. You won't know everything. No math instructor knows everything. The math instructors know the things they're currently teaching. So if let's just say I hadn't taught differential equations in 10 years, and you're in DiffyQ right now and you had a really gnarly problem, you came to me. I'll be able to help you, but I won't be able to help you maybe as good as if I'm teaching it right now. You guys will come to me with physics questions, which is really funny. Yes, I had physics. Let's see, my first semester of physics, Reagan hadn't been sworn in yet. And you're going to ask me a physics question. I can help you a little bit, maybe the first week or two of the semester, but I had, like I said, I had physics a few presidents ago. In fact, I had it so long ago, the law of gravity was still before Congress. It wasn't actually a law yet, but I can try to help you in physics, but I'm not doing physics. So why would I know the answer? I know the answer to the stuff I'm teaching. You know the answers to the stuff you're doing. But it's the fringe stuff you want to make sure you're not discounting, because the further you go, the people around you will also know the fringe stuff. And what I mean by fringe stuff, I don't mean this necessarily. I mean your 20 integration formulas on your sheet. The ones that are less common you still want to be aware of. Integration technique you want to be aware of. Number one by a mile. What have I already said many times? What's the number one integration technique by a mile? We've learned in this class.
Partial fraction.
Parts. Parts is huge number one. That's the one that shows up over and over again. Partial fractions decomposition has a tremendous role, but strangely enough, not so much in integration. It's just standard problems that I need to break things up. It shows up a lot later on, but less as an integration tool, strangely enough. Okay, so those are the things. So let's start this one. Okay, so cosine 1 minus u squared over 1 plus u squared. And on top, I'm going to have 2 over 1 plus u squared. I don't know if this is going to present a complicated integration or an easy integration, but I know that's what I want. And I know that's a rational function, so I have confidence that I can at least start the problem if I can't finish the problem. I can at least get it to the point where I'm stating an integral that can be integrated even if I can't remember the details. Simplest thing, and I always like doing the algebra off to the side. I don't like writing integral equals integral equals integral while I'm simplifying the integrand. I'd rather simplify it separately. I can do this in exactly one step. There's only one denominator in each numerator denominator, and that's the 1 plus u squared. So just do that. And that's the only step you should be doing. A lot of us will waste on, let's find this over a common denominator, let's do all that, then we'll flip over and we'll multiply. All of those are correct, but you're talking 5, 6 steps. No, I want to do this in one step. Why? Because I can, and I'm not going to make any mistakes by rewriting things, getting numerators and denominators mixed up. Multiply the numerator by this, and what do you have now? 2. Multiply the denominator by this, and you have 2 times this. Those cancel. I'm going to put parentheses. Careful, because that was a minus sign. Can I clean this up? Won't that be plus, I'm sorry, minus 1 plus u squared? Yes, no, maybe? I'm subtracting the quantity 1 minus u squared. So is that right? Okay, so now what do I got? 2 plus 2u squared minus 1 plus u squared. That's 2 over 3u squared plus 1? Or 1 plus 3u squared, doesn't really matter which way you write it. You know what, let me write it the other way. Might be more recognizable. Okay. Oh, this is going to be gnarly. I'm going to have to do all sorts of crazy substitutions. Or not. Can we give the answer as the very next thing we write? Yes. Because this is the form of what? Inverse tan. Oh, I don't have to do anything. But I think it's always wise to do things like this. 1 squared. Is that true? So what do I need on the top? If you think of this like a u substitution, I need a root 3 on top, don't I? Does everybody catch that? I need a root 3 on top. Now, here's a trick that some of you would like to do, and this is absolutely correct. You said, let me multiply top and bottom by 1/3. This is absolutely correct, absolutely valid. Now what do I have? 2/3, which is just a coefficient. That's going in front. Don't let that get in the way. But then what do I have? 1/3 plus u squared. Oh, I like the u squared. Oh, but that's, what is that? That's 1 over root 3 squared. There's my a squared plus u squared. You might find this one actually easier. I'm going to get the same answer in the end. Okay? Can you tell me what I'm going to get in the end? Well, my numerator is going to involve, I have a 2/3, so I'm going to pull that out in front. I don't want that in the way. Okay? Then let's write it as 1 over, 1 over root 3 quantity squared plus u squared. There's no chain rule factor at this point. So this is an inverse tan. I'm going to mold the board here. Let me get rid of this. We know this is inverse tan. And there's a u involved. I'll put it right there. My a is 1 over root 3. So what goes right here? Root 3. What goes right here? Also root 3. Can I write that 2 root 3 over 3? Could I write that as 2 over root 3? Would that be the same thing? Neither are rationalized, one of them is simplified. And you were lied to. That's simplified, that's not. Rationalized means you have no roots in the quotient. It matters not whether it's numerator or denominator. It has nothing to do with it. But because I have a 3 to a power on top and a 3 to a power on the bottom, this is not simplified because the root 3 cancels. That's simplified. Neither one's rationalized. I could care less which one you use. Use whichever one you come up with first. I would probably opt for the second one. And that's my answer. No, that's my antiderivative. What do I still need to do? Replace this with what? What's the identity? Cosecant minus cotangent. So your answer is going to be an inverse tangent of a cosecant minus a Does that feel evil? Oh yes. Oh, that is a most evil answer. By the way, do not check that through differentiation. That's where you go online and use a source. That would just be too awful. If you put this problem though online and ask for the antiderivative, I will go out on a limb and say there's not even a possibility you're going to get what we get. You're going to get a version that requires a lot more work to get us there, and it won't be a useful version, and it'll probably have the tangent of a half x in the answer, which again is not useful to us. So the final answer is going to be root 3 times cosecant minus cotangent. And it's an inverse tangent of that. Yeah, that's a horrible looking answer. But really the key was that this integration wasn't tough. I could do it this way, and then I make sure that I do root 3 on top and bottom because the chain rule factor. Or I said do it the other way, make it u squared and then have a number in front. I think most of us would find that one easier, but it's an extra step. It doesn't make any difference. So, okay? This is evil trig. I'm going to ask you a question of evil trig. Now, where are we? We are finished with the material for the first exam. The first exam is primarily going to be methods of integration, obviously. There is some application. The exam is still a million years away because I always do it 3 classes later, so you have time to get all your quizzes turned in. A week from today, you'll be turning in the quiz from today's material, and we'll be doing our review. Then we will have the exam. The idea is you will not take the exam before you have turned in every quiz that's on the exam. The practice test has been up for a while. I don't expect anybody's looked at it yet. But starting this weekend, you might want to consider looking at it because we've now covered all the material that's on there. Don't look at it before you do the quizzes and stuff. No, finish the work for today. Completely finish today's stuff. Then look at the practice test. And the reason is really important. I was asking some of my folks in the higher class, I said, when you guys do the practice tests, how did you do them? One person says, oh, I just do them as I go. You know, I do them over the course of like 4 weeks. Each lecture I knock one off. And I'll say, how do the exams go? And they say, oh, sometimes they're kind of rough. Then I ask someone else, they say, no, I sit down, when I feel ready, I sit down and do the whole thing in one sitting. Then I kind of laugh and go, how's it going? Well, they got an A in every test. These got a high score in every test. They just told you what to do and what not to do. You're not going to take your exam over the course of a month. Don't take your practice test over the course of a month. No, do your practice test in one sitting. Then, if you can get through things, you go, I got that one nailed. On the practice test, I generally make it the shortest collection of questions that literally covers everything. There'll be 1 parts, 1 trig substitution, 1 partial fractions. I can ask you more on the exam, but if you can't do the partial fractions, then you need to go back and do more partial fractions as practice. Okay? But if you're doing it over the course of a few weeks, that's really artificial. You need to do it in one sitting, and then when you come up with problems, you can fix them now. We will review next week, so the only thing that matters is you have finished the practice test before next Wednesday's class, because that's the primary point of the review, is we go over, and the best part is 90% of the questions you would have had, you've already answered because you went over the key and said, oh, okay, I made a mistake, that's how I'm supposed to do it. The question is, okay, I did it that way, how would I have known to do it this way? Could I have also done it this way? Things of that nature. I got to this point and I didn't know what to do next. The one question I don't like is, you go, can you do problem number 1? Well, you have a detailed answered key, and so when I do it, I'm gonna do it verbatim exactly the same way I did it on the key. I won't do it differently. So you're not getting anything out of that. So what is it you didn't understand about the solution would be the question. Not, can you just simply do the problem for me? You have it in front of you, right? That you don't need me to redo it, but pick it apart. But you have a whole week to get that part ready, okay? And I don't really want to talk about the exam much until we're reviewing next week. And then basically don't leave if you still have questions. Let's go.